Alright, so we have last Monday looked at Jacobi's method. And this slide pretty much summarizes it all. So basically our attempt we need to find an alternative for large systems. Let me just swap this place. All right. For large systems, we need to find an alternative to Gaussian elimination, because Gaussian elimination, there's a lot of round of error that piles up during the calculation. We have looked into the complexity and how long it takes. So basically, we need to look into some methods that are not necessarily looking for exact solution, which Gaussian elimination, if you didn't have round-off playing a role, you would get an exact solution to the system, but possibly an approximate one. Nothing wrong with that. Most of the numerical methods operate in the sense that they're looking for solution that over the iteration gets better and better and gets close to your actual solution, though not precisely the solution itself. So one such example is so-called Jacobi iteration. It's really motivated by just rearranging your system. So if I rearranged my linear system so that I leave, basically in the first method, I leave x1 on one side and put everything else on the other side. I leave x2 in the second equation on one side, put everything else on the other side. When I proceed and do that for all of the x's in my vector x, or elements for vector x, I get a system for a 4x4 system, I get a system like this. And this generalizes to one formula like this that looks a little bit cryptic, but it's easier to actually write down a more general algorithm that works for a system of any size, in this case n. Okay. Now, basically in each iteration, so I start with a number, with a vector x that has elements, in this case 4 elements, but it could be any elements. And those are my so-called old iterations that I work with, and I plug into the right-hand side in order to get my new iteration. Okay? And then I look at the error between the two, and that error in each iteration should get smaller and smaller. So I basically stop when my error is small enough, if this system indeed converges. This is sort of the core idea of numerical methods. Often we arrive at the numerical method just by looking at the problem, rearranging it a little and hoping it works. Okay? There's a whole another proof that we're not going to do that basically says that for certain systems and for certain matrices A that are so-called diagonally dominant, this method will always work. Okay? So that's a whole another element of analysis, typically left to numerical analysis, which maybe you will be, maybe you will not. Most likely you will just use the methods. Okay? So basically there's an entire set of scientists that are working on proving that methods actually work and that they arrive at the solution within with certain speed and certain accuracy. Okay? Now we're not going into a lot of that. We're just really introducing ourselves to numerical methods. And then basically we go and apply it. So I asked you to do the computational assignment. Has everybody completed it? I'm going to review it now. So if you haven't gotten the chance, now is your chance to wrap it up and actually submit it. So when we're solving this example system that is 3x3, I always need an example system. Last time, I can use Python as a calculator and just plug in. This is my calculation of the new vector. 0th element by this is my b of 0 minus elements of a multiplied all other elements of my old iteration x, and I similarly proceed with 1 and 2. So basically when I executed this, I got first and second iterations that already got pretty close to what I claim on my slides is the actual solution of this system. Now, if I wanted to program this, I completed some of this, but part of it is still left to finish here in front of the class. So basically, my iteration, I pass my matrix A and my vector B to my function, which I called Jacobi iteration. I also give it input x old and tolerance. What do I need to do? This is a programming tip, or maybe you remember it, maybe you don't. If I wanted to introduce some default values for x old and tolerance, what do I need to do? So I actually give it a value, say equals 2 and the value that I wanted. So if I don't provide it to the function, it's going to take that value, which is really kind of cool. Okay? So it's going to assume the value, so I can actually say, hey, if I don't give you anything, just do zeros of B shape. How's that? And if I don't give you any tolerance, use 0.001. But if I provide an alternative, yes?
So you couldn't set it to n because it hasn't been defining the function yet? You couldn't have done x old is equal to np.zeros of n?
Yeah, n hasn't been defined yet. Yeah. So I'm using something that I have. So this is how do you define default values that are just then going to be taken into account if you don't provide anything. If you provide something, that something will take over, okay? Great. So first things first, I want to compute x new. My computer doesn't know what x new is, so I have to give it some memory, okay? And that is done, I also zero out all of that memory. So these values will be overwritten. What do I initialize it with? Doesn't matter. Okay? And then my n and m are shape a shape. This m better be equal to n. I'm right now not checking, but it's a good programming practice to check. And then let me just, in the programming, let me just define these new values just like I would in this general formula right here. So basically, for all of the i's, I have to have a for loop that loops over all of the elements, new elements that I'm defining. I'm going to define this new value as b minus some mysterious sum divided by a of ii. Okay? And that mysterious sum is actually sum of all of the other elements of x and the appropriate element from matrix A. So when I want to write that down, I will write as follows. Basically, if nothing, you can just write down this. My x new of I is this b of I minus that mysterious sum, which I call my sum, and divided by a of ii. And here is how I compute the sum. This is our exercise from exam 1. So technically, I'm not going to on exam 2 test you on exam 1, except that I will, because if you don't know how to write these sums that we practiced back then it's a little hard to solve this problem. So every sum is initialized with 0. And for all of the other j's that are not equal to I add to the sum a of ij times x old of j, which is what the formula is telling me to do. And I wait for the sum to be completed. This for loop will execute completely. And after it, I'm going to have sum. It's important to initialize the sum to 0 at every step. Otherwise, you're going to be carrying over values that you don't want to carry over. And this is my x new. Great. Now I have x new. And I compute the error between x old and x new. I can just use np.linalc.norm. We all know how to compute norms. By default, this is going to be 2 norm. I can also specify a different norm, 1 norm, or something like that. Specific norm you use, doesn't matter. quite frankly, your algorithm converges or it doesn't, and maybe plus minus five iterations, that's not going to change anything for using different norms. And I need to divide this norm by norm of x new or x old. I can pick either x new or x old. I tend to pick x new simply for the reason that if I start with a 0, I'm not going to divide by 0, though I'm here checking this new, and if this norm is different from 0, then I divide the error, otherwise I skip the division by 0. That's just a safety check. I did not do safety check here. I should. If a of I is different from 0, then you do this. Otherwise, at this point, just say something. Print a of I is 0. Do something. So this really is just my semi-lazy way to give myself a warning. I'm going to do something really if on some further testing this happens. And then I have to deal with it. But at least I have some idea of where the problem is. Okay, so this is my error. And right now I'm going to test the code before I proceed. So I'm just going to return this x new. So what I did right now is just defined my new value of x based on the old one. So that's basically one step of the iteration. I'm not iterating yet, but I want to test whether it works, and I want to test it on this method that I did by hand before. So I define my matrix A, I define my B, I actually here provided x old, and the tolerance, and I'm going to print this x new after one iteration. And I think I got the same as in the previous case. Yes, I got the same as in the method by hand. So I did something right. So this is just showing you, even if you've completed this, how you kind of complete step by step and test it step by step so that it's easier to debug your program. Excellent. So I have this thing done. Now I need to actually figure out how to iterate until my error gets smaller. I'm going to post the code, plus the video, so taking pictures possibly not needed. Okay? So now I need to actually iterate and say, okay, while my error is larger than tolerance, do all of this. So I'm going to indent it. Except that coming in here, I don't know what error is. So I'm just going to say, well, error is 10 times tolerance. So I'm certain to enter the loop at least once. Yes? We're just initializing error. It is also always a very good idea. There's no guarantee that this is going to converge. So I'm going to count my iterations. And I'm going to give myself a maximum so I'm not sitting here in an infinite loop. So I'm going to say, and my iteration is less than maximum iterations. So this is going to be, make sure that it stops in case the whatever A I provided does not converge. So this is sort of a standard programming practice with while loop that is simply good coding practice. So kind of embed it in your memory and just use it. And let's see whether this works now. So I'm defining my new x new, and I tested one step. This seems to be working based on the x old. Then I compute the error between my x old and x new. Excellent. So what else do I need to do? So now if I'm done with this loop and I just proceed in my next step, what will happen if it's programmed as this is? If I now start this program, what will happen on the next? So first iteration, I know I provided it x old, it gave me x new. That x new is this one, 2.6 minus 2.75, 7.14. It's going to compute the error, and then if I go again, my x old is the same as the x old I started with, 0, 0, 0. My x new is the same as this one that is, it's going to be the same as this one that is computed. So it's just going to keep doing that. And good news is that I have a checked iteration less than maximum iteration, so it's just going to stop after 10,000 of those without actually moving along. Does that make sense? I can actually test it. And I'm going to print the number of iterations before I return. Print iterations. So it's doing this for 10,000 times. Ah, is it going to be just 10,000 times? Which other bug do I have? It's not stopping. Why?
Because we didn't give it a break.
We did an increment iteration, right? That's one thing. So that's one mistake. So when you enter here, please increment. Okay. And now it actually did stop at 10,000 times, but didn't move my x along. Why not? I never updated x old. My x old is the same 0, 0, 0 that I provided at the beginning. There's nothing changing x old here. If I don't change it, computer will not change it on its own. The computers are actually extremely dumb. Okay? Unless you tell them precisely what to do, they aren't going to do anything. So basically here, I should say, well, update my x old. It is good idea to use np copy of x. So this x new value, simply copy its values into x old. I could also use a for loop to do that. It's just that there is... so here I did this, right? I'm not going to write this down n times. I would need a for loop to do this. But instead of doing that, I'm already using a function that does precisely that. One could technically write x old is equal to x new. In this case, it would work. The problem with that is that in that case, x old is assuming the address of x new. Name of an object in Python is its address. So this x old simply starts pointing to the memory of x new, which will actually in this case work, but sometimes if I actually want to use those values as separate, it's going to be a problem. And in this iteration, I would have an issue because I would actually look at the... No, I actually wouldn't. In this particular case, it would be okay. But this simply copies the values of x new into x old without changing anybody's address. In memory, they still remain two separate places that store different values. Excellent. So this is actually should now work. Let's see how many iterations until I get the accuracy. 4. Okay? And after 4, I'm within 0.001 tolerance. Now if I actually execute this with a little better accuracy, so now whatever I provided here will overwrite the default value. I need 5. It's still pretty cool and pretty fast. Yes? And it's still less number of computation or less number of floating point operations that I need to do than I need to do for Gaussian elimination, even in this problem. Yes?
Isn't that due to the nature of the matrix you're analyzing? The diagonal domination?
Yes. So that it's a very diagonally dominant, and that makes the problem much speedier. If I actually probably put, let's do a quick test. If I probably put a little lesser numbers here, so it's less diagonally dominant, I'm just gonna, now I don't know what the actual one will do in all cases, right? Let's see whether that increases the number of, a little, by 3. Okay, this is a small problem. Let me return it to what it was. 3, 7, and 10. Okay, questions about Jacobi method and how it works? Again, if you haven't gotten the chance to submit this code online, do that by the end of the class. Okay. We will just briefly comment on some more methods. You will actually get more practice of this in your homework. So people by nature are greedy. Even when we improve something, it's never enough. And there's actually a way to speed up Jacobi method. So Jacobi method is speeding up Gaussian elimination. Now we want to move on. And there is one school of thought that says, okay, let me look at, this is a standard Jacobi iteration. This is how I would write the code. At x1, it's fine. All of the old values are old values still. But once I compute my new x1, a greedy person would ask, well, here on the right-hand side, why not use that new value for x1 and old ones for all the others? Okay. Let me look at this code that is doing Jacobi method in 3x3 case. I'm essentially asking here, okay, I'm computing my x nu of 0. This is all great. When I'm computing my x nu of 1, I already have a new value for x old of 0. I just computed it in my previous line. A greedy person would ask, well, why not use a new value right here? This one that I computed in the line before. Okay? An old one where I don't have a new one. Okay? And then in the next line, I have new values for both of these. Okay? Can I use the new one? So what would GaussSeidel by hand do here? I'm going to copy all of this. And I'm going to say GaussSeidel by hand. Okay. So here, since I have a new value, I'm going to use a new value. And here, since I have a new value for both 0 and 1, I'm going to use a new value. So if you remember, this was 7.14. I'm actually closer to 7. So it appears I'm getting there faster by this greedy method. So basically, comment here is I have computed x nu of 0. Use it instead of x old of 0. And here I have computed x nu of 0 and x nu of 1. Use them instead of x old. So for whatever updated value I use, I can use it. And it appears, at least for this number is closer to 7 than my previous, this is what I had before. At least here, I have definitely improved and gotten closer to the 7, even in one step. Does the logic make sense? It's pretty much just the greedy logic. I have it, let me use it. And that, indeed, in many cases, speeds up how fast and how many iterations we get to the solution. So again, I just took the code by hand. This was my calculation by hand from last time.
Well, if we did exactly what you did right there, should we have the same answers or no?
You should, yes.
Slightly off. First one's the same, the second one's not, neither is the third
So,
one.
and after the second one, they would both be.
Yes. So at the this is my last one, where I've already computed all of them. So if I had n of them, this last one would have all of the new values.
And in the new one, the old one,
Uh-huh.
which one would
This one?
be that one? No, that in the bottom one?
Well, it's-
Bottom one?
So,
The middle one. The middle one?
The middle one, it has one new, one old.
The old one, which one?
X old of 2.
Out.
If I had more than 3, there would be more values here, new and old, right? Did everybody get this?
No.
Stop.
So if it was.
So if you are finished, if this is working for you, you can start modifying Jacobi's for GaussSeidel because that's going to end up being homework.
Sí, o sea, es como
I'm wondering if you could be able to use this code, because this is where you define the iteration. They were those ones, I don't have them.
So execute your, yeah, all it needed is, there was no definition of execute.
Because that's right here, and you didn't copy the word.
So yeah, this is a standard little thing. If you rebooted or something and you did not execute that import numpy, define x old, define x new, it's gonna yell at you with some name error. So these things you need to redefine or just execute this cell before you execute your code. But I'm actually defining it, but I'm not importing numpy again.
So if it was a 4x4 system, we'll have the first 2 lines, and the third one will be the same as the second line.
Well, there would be also the x old of 3, right? So there would be an x old of 3 used here. Here I would have x old of 3, so the first one would be new, the other 2 would be. Then I would have here, I would actually have an old value, x old of 2, or x old of 3, and then I would have one more line for x new of 3. Okay? So in case of n equations, I would have n those lines. So along the similar lines, basically, you can modify this code to create GaussSeidel method. That's going to be your homework. But basically, I'm going to point out that here, whether you're going to use x old here or x new depends on whether j is larger than I or smaller than I. Okay?
Can you scroll up a little bit, please? On that same.
Where do we have a problem?
So the Jacobi Iteration, the definition part, you are saying XL equals to beta zeros beta shape. However, we cannot call B at this moment.
Oh, okay.
Mine says B is not defined.
B is not defined. So then we need to just provide zeros, but the problem is like I need a shape. I can define n before that, but that's not as clean. So,
I just don't understand how, I don't understand how if mine looks exactly like yours, how yours is.
because I was actually giving it a value here.
Because it's already in the computer memory.
So no, but I was providing it xsold, so it never executed this part. Did everybody else have a problem with xsold equals to B shape? I don't know. What is the do you know number of arguments? Can we go with this? That type of code?
Yes, but you should.
Nah, I don't want to go there. Yeah. Okay, so we'll just leave it at providing tolerance. If the B shape, though B shape should have worked, but okay. Because we have B right here. Hey, yes?
I have another question.
Yes.
How come in the last line it's x mu of 0 instead of x mu of 1? Which is the case?
It is both.
Oh, that's
I have to use both. All of them. This is, you know what this is? I often actually leave spaces, and here I wasn't. This, to me, helps a lot. Just putting spaces in between operators and actual numbers goes along, and I was typing in fast last time, and I didn't do that. Okay. There is one more version of this. Just like in root finding methods, these type of things, you kind of have to test them on the systems that you're going to be working with and figure out which of the methods works the best. There's one more method that basically is called Successive Relaxation method. And it's going to take a lambda, whatever lambda is, times my x nu, and 1 minus lambda, so it's going to do a weighted sum of your new and old value, again in hopes of speeding up. This is something, again, that has to be tested on systems that you want to use, and sometimes you will actually have the systems and know what those systems are. So you kind of find which lambda works the best, and then you go with that lambda, okay? And that's what you implement in your code. So there is, if you have lambda between 0 and 1, then there's weight, certain weight placed on the previous or value. And if lambda is from 1 to 2, then there is more weight taken for the present value or new value. And that's going to be the homework. So in a summary, we have direct methods, Gaussian elimination. LU decomposition is an attempt to speed up Gaussian elimination when we were executing it a lot of times for same matrix A. There's no error if you actually use proper fractions and you don't have round off during your calculations. However, on computer we don't have that, so round off will create errors. And those errors become problematic as I have very, very large systems, typically with more than 1,000 iterations. In those cases, I switch to iterative methods. This is just a sampling of them. There's much more of those methods. There's an entire sort of scientific branch looking at solving systems using iterative equations. And Jacobi is the base method, where we basically just rearranged our initial system to kind of motivate a numerical method, and it seems to work for certain types of matrices A. And in that case, I arrive at my solution much faster, so I will have less of those round-off and truncation errors due to smaller number of iterations. So this is typically faster than Gaussian elimination than for n is larger than 1,000. So now we will, before finalizing this, we're going to start working with some examples on how to formulate a system of equation. And I'm going to start with a classical. Is everybody in differential equations? Was. So everybody knows a little something about differential equations, which is excellent. Okay. So we will look at solving the differential equation for a heated rod. Heated rod. So my model is as follows. I have a wall on one side. I have a rod and wall on the other side. My wall on the left is at T0, which is 40 Celsius degrees. My wall on the right is at 200 Celsius degrees. And this is 0 meters, this is 10 meters. So I have a rod that is 10 meters long. And I have ambient temperature of the air, which is T air, which is 20 degrees. I have much more heat here, less over here, and I'm constantly supplying heat to these walls. Okay. So in nature, things tend to equilibrate, so you will always flow or have a flux of something from wherever you have more of it to wherever you have less of it. Okay. If we have water and we pour water and we give it a potential, it's going to flow to wherever there's less potential or pressure. Okay. That is momentum transfer. In this case, we will have flux, not necessarily of particles moving along, but due to the molecular motion that is much higher here because of the higher temperature, that literally through molecular collisions is going to transfer, so that is the heat transfer, and there's an energy flux per area, from area of larger flux to area of larger temperature to area of lower temperature. Okay? So the difference in temperature, there always has to be difference of something to get the flux going. Huh? Great. I actually have, and then not only that, this is not an insulated system, so I'm going to have a heat loss to the air, because air is 20 Celsius degrees, and the rod, well, the walls are 40 to 200, right? So I can already see that it's not necessarily, if I had nothing, I could just say, well, what is my temperature going to be? I can just plot a linear function between 40 Celsius degrees and 200 degrees, right? And that's kind of an approximation of what the temperature should be in some sort of equilibrium situation in between those walls. But the problem is that I have loss to the air, so that's going to create it sort of a non-linear. There will be more loss to the air, so there I expect my temperature to be a little less than that. Okay? Excellent. Now, somebody else has already come up with differential equation for this process. That's going to be in your transport phenomena class, which is something you can look forward to next semester, I believe. So basically, there's a temperature equation that says that second order derivative of x, x is this direction, plus I have a heat transfer coefficient h between my air and my material that the rod is made out of, times T air minus the temperature of the rod is equal to 0. So I have approximated my rod with a one-dimensional system, and I'm parameterizing my x from 0 to 10 meters. So this is essentially my what I'm going to call x0. And it goes to 10 meters. And this equation, so this is heat transfer coefficient between rod and air. And these are literally measured in the lab with different types of materials. So it depends on the material that rod is made out of. And this is something that is measured in length to the minus 2. So 1/meter squared. Okay, so how do I actually solve? So this is a differential equation. In your ODE class or whatever you did differential equations, you would look to find analytic solution to this equation. That analytic solution would be temperature distribution T of x, right? That whatever x, it's a function. I give it an x and it spits out the temperature T. Numerical methods don't do that, okay? They first discretize this system, and by discretize, I mean find a number of points along this rod, label them, and then look for solutions just at those points. That's called discretizing the domain. So we're going to discretize this domain, okay? This is going to be, well, my x0, x1, x2, x3, I decided to have actually less in my problem to have a smaller system. And x5. So this is my x0, x1, x2, x3, x5. So those are my locations. The simplest way that I always do is that I space them out equally, right? So that lim space command will come in handy, or arrange, or both, whichever you choose. And I'm looking for temperature T0, T1, T2, T3. How did I, is anybody checking on my counting?
4.
This is a result of me not having coffee this morning. 1, 2, 3, 4, 5. Like 1, 2, 3, 4. 1, 2, 3, 5. My daughter went the other day. 1, 2, 3, 4, 5, W. With the W, she's enchanted with W right now. She's 2 years old. But obviously, concept of counting, there's some sequence in there, but the meaning of it is not there. Anyway. So I'm looking for T1, T2, T3, T4, and this is my T5. Okay? So these are my X's are my spatial locations, and my T's are my temperatures I'm looking for. What is T0?
40 degrees.
What is T5?
200.
There we go. Those are my boundary conditions. You love those, don't you? In differential equations. So those are my boundary conditions. Okay. So numerically, what do? I know that just like for everywhere else, my differential equation has to hold at these locations, T1, T2, T3, T4 that I'm looking for. That's what I'm looking for. My temperature distributions will be these 4 numbers. Okay? If I want more of them, I can put more of them in there, but that's too much to write. So I'm just going to stick to 4. Okay? So my result of a numerical, so we're looking for a numerical method. To find T1, T2, T3, T4, which are also T of x1, T of x2, T of x3, or T of x4. Same thing, right? And I know that my differential equation has to be valid at those points just like all the others. So what we're going to do, we're going to approximate this with a numerical version of it using these values and plug it in. Now we have already had those so-called finite differences. We have already introduced, I believe, in some examples that my approximation to the derivative could go like t of at some x, t of x plus delta x minus t of x minus delta x divided by 2 delta x. Does that look familiar? Or dt dx is t of x plus delta. This one is probably more familiar. We use this all the time. That's the slope or linearization just at that point. It's really slope between those 2 points, right? So these are called finite difference approximations to a derivative. The top one is a central, the bottom one is a forward. There's also backward. So the third one is this. Well, good news is I have one for my second order difference as well. Technically, you can now go and approximate this and this also with these 4 differences. And you're going to get that the second order derivative can be approximated as t of x plus delta x minus 2t of x plus 2 of x minus delta x divided by delta x squared now. What a timing. Okay. So what we're going to do is we're going to take this and plug it in instead of that derivative and use these T1, T2, T3s, T4s at every point to form a system of linear equations for T1, T2, T3, T4. Yes? So that's going to happen on Friday. I have already announced that my office hours from now are moving to Friday. So please bring your questions.
For this test,
Is that